Yes, we can see it.
So that's the distribution. So, so it says upper alpha probability points control F distribution with N1 degrees of freedom, that's df in the numerator, and N2 degrees of freedom in the denominator. So N1 is here, so these are the numerator degrees of freedom, and then N2 is here, these are the denominator degrees of freedom going down. And then what this table does is it has put the upper tail probabilities here. So there is a 0.1. Okay, so there is 0.1, then 0.05, 0.025, and they are getting smaller. Okay, so that is the F table there. So what you notice on that F distribution table is that we don't have values of alpha in the upper tail exceeding 0.1. They start from 0.1 and get smaller. So if we are looking for anything bigger than 0.1 in the upper tail, we should apply some property, which is this property here. So this note here we are saying the F distribution only gives F values for small upper tail probabilities, such as 0.1, etc. That's what I was saying there. So if we want bigger upper tail areas, we need to look at the complements. So the relationship here is F of alpha on mu1 and mu2 numerator and denominator degrees of freedom is the same as the reciprocal of the complement of this alpha here, and then we switch the degrees of freedom here because we're getting the reciprocal, right? So it means the degrees of freedom are going to switch. What was numerator becomes denominator and vice versa. So that's the one that we are going to use. So here is an example. So a college mathematics department was considering 2 screening exams for the purpose of placing students. So we have students in 2 sections of an introductory maths course that we are given a test, and these are the results obtained. So in section A, exam 21, and their sample variance was 121. For the other section, B, the sample size was 16, and the sample variance was 64. So what we want to construct for, we want to construct a 95% confidence interval for the ratio sigma squared A over sigma squared B. So in short, the ratio of the population variances, and then in Roman 2, the ratio of the standard deviations. We want to find a 90% confidence interval, or basically the opposite of what we are doing in A Roman 1 there. And then we want to answer the question that the 2 population variances are different. So remember earlier on, we are saying when we are comparing 2 means and the population variances are not known, we can either assume they are known if we are given the equation, or we can carry out a test to determine whether they are indeed different. And we are going to do so right here in this example using this confidence interval. Okay? So here we go. So let's use 1 and 2. Even if it doesn't matter, we can still use A and B. But here I'm saying let's go sigma 1 squared sigma A squared, sigma 2 squared sigma B squared. So N1 when instead of using A and B, where there's A we'll put 1, N1 is 21. The corresponding sample variance is 121 for section B, which we are calling 2. The sample size is 16. The sample variance is 64. And then we want a 95% confidence interval. So alpha is 0.05. And then this is the expression for the confidence interval. So the ratio of the variances divided by this. This is an F distribution, giving an aperture area of alpha over 2, n minus 1 degrees of freedom, n minus 2 degrees of freedom numerator. And there is basically just a complement of this alpha over 2 here, 1 minus that. And then we put the values. The variance for the first sample, 121. The variance for the second sample, 64. Alpha, this is a 0.05 95% confidence interval. So we're dividing that by 2.025. And then N1 is 21 minus 1 is 20. N2 is 16 minus 1 is 15. And then that's the ratio of the population variances. That's the same thing that we have there, except this is 1 minus alpha over 2, so 1 minus 0.025, which is 0.975, 20 and 15. Numerator degrees of freedom, I mean denominator, numerator and denominator. And then to now go to our F tables. So we are saying 20 numerator, 15 denominator, giving an aperture area of 0.025. So here we go. We say again, no is ratio. We said what? 20, 15. 20, so here is 20, this is the numerator. 15, so I need to make it a bit smaller so that you can see here. Except too small again, but here, so 20 is here, the 15 is here, and the probabilities are here. So we are going on 1, 2, 3. So the third one. So this is the third one. So the 20 is here. Are you able to see, or do I need to zoom?
Zoom.
Yeah. Zoom in.
Zooming, eh? So we are here. Okay, so let's zoom. So it was 15, eh? 15, except now I've forgotten where we were. I should have highlighted. So let's do this. So 20, 15, where is that? 20. So this is 20. 20, 15 is here. Does it highlight? It doesn't, eh? So, but anyway, 2.76, so 2.76. So 2.76. Yeah, are you able to see this?
Yes.
This value here, 2.76. Okay, so that's the value. So that's the 2.76 here. And then we don't have a 0.975 there. Okay, so what did we say? We get the reciprocal of this, right? When we get the reciprocal, it means it is going to go up, and then we'll get the complement of this. So subtract this one, get a 0.025, and then we'll switch the 20 and the 15. So now it becomes 1520 0.025. So 1520. So 15 here is 15. So 15 is here. Where 20? So 15 is here. 20 is somewhere there. Okay, so am I able to see 2.57? 2.57. Are you able to see the 2.57? Right there.
Yes.
Okay, so that is the value we are going to 2.57, and then we multiply. Okay, then the second part, we want the confidence interval for the ratio of standard deviations. And just like we did for the variance, one variance, these are squared, the standard deviations are square roots. So basically just square root all these. Yeah, so it's basically square rooting the endpoints. So the ratio of the standard deviations is going to be in between those two. Okay. And then part B, what are we doing in part B? We want a 90% confidence interval, but we have reversed the row of the variances. So if we do the reversing, first of all, it's a 90%. So a 90% means we have a 0.9 that we are subtracting from 1, we get 0.1. And then they are the other way around. So 1 squared. So even these are the other way around. So in short, where there was SC1, we put S2. Where there was and vice versa. So it's basically we have switched the row of these two. We have also switched the row of these two. We have switched the row of those two. So that's the so everything is. So that now we have 64 over 121, except this one here is 0.1 divided by 2, so it's 0.05. It's now 1520, and okay, 1520. When we subtract it from 1, we get a 0.95, and then so basically, I think you have seen how to read these, right? So now we go under 15 numerator and 20 denominator, and leaving an aperture area of 0.05, we get a 2.2. And then we don't have a 0.95, so we are going to get a reciprocal of this, meaning it will move from being in the denominator to the numerator, and then we'll get the complement of 0.95, subtracting it from 1, get a 0.05, and then we switch this, so it will become 2015. Then we read from the F tables, and that is what we are going to get. Okay? Then finally, part C is we want to check whether the population variances of the exams are different. Okay, so let's look at this confidence interval here. What do you think? Can this interval help us answer that question? Are they different? Ladies and gentlemen. Hello. Are we still here?
Far away.